Welcome to the very first lecture of AP Physics. Today we'll be covering some of the topics from Chapter 1 of the textbook. So first, science is an ongoing process with new discoveries being made all the time. Most of these discoveries follow what we call the scientific method, where you may make an observation, develop a hypothesis, test that hypothesis, and eventually that may lead to a law or theory. In science, a law is a more basic sort of description. It may describe the relationship between two variables. So for example, Boyle's law from chemistry, or Newton's second law, F equals ma. Those are nice examples of just basic relationships. A theory explains why that relationship exists. So for example, there's a universal law of gravity, which is an equation. And then Einstein developed a general theory of relativity, which explained how objects with mass warp space-time. So that describes how gravity acts. You should also know the term theory is used differently in science compared to how it's used outside of science. So outside of science, when someone uses the word theory, they may just be describing someone's opinion or idea. And in science, a theory is something that has been proven to be true through multiple tests and experiments. So a scientific theory you can think of as being essentially a fact, right? It's our best understanding of that topic. It's not someone's just guess. And in general, you should know that this method is not always followed linearly. There's a lot of times where you may be testing something and you may make an observation that you were not anticipating, and that can then cycle back and lead to some new law or theory. So physics comes from a Greek word that means nature. So we study the natural world, but typically we are looking at larger objects. We're not looking at living plants or animals in this class. For this course, you'll need a working knowledge of basic math. We'll cover some of that basic math here today. You should also look at Appendix A to see if there's anything there that you're not confident with. It's not just being able to use this basic math, but applying it to new situations. Graphing is very important, both graphing your own data and then taking a graph that's already there for you and analyzing it, figuring out what it tells you. SI units will be used. Sig figs are not super important for this class. We will cover it this chapter, and then after this chapter, basically you just need to be able to give your answer in a reasonable number of sig figs. So what is a reasonable number? I would say 3 or 4 sig figs is great. 2 is acceptable. 1 sig fig or 5 sig figs is really pushing it. More than 5 sig figs and you're likely to not get full credit. This is true for labs as well as for exams, including the AP exam itself. So don't write an answer as 51.372568, because that implies you know that value much more precisely than you probably do. Common sense is super important. A lot of our problems you may be able to picture in your head. So if what you're picturing doesn't make sense, then that may give you a clue that you've made a mistake somewhere. And last, persistence and patience are very important. So Evie and I, if I come across a new AP Physics problem, I'm not always confident in the best manner of solving that problem. So for example, maybe I'll try solving it with equations with forces and motion. And then later on, I'll realize it would have been a lot easier to use equations with energy. So don't give up if you reach a dead end in your problem solving, or if you don't get the correct answer on the first try. All right, so going into some details now. Most of today are things that you've probably seen before in a previous course, so hopefully this is review. So precision is the repeatability of a number. It's how close your trials are to each other. So if you're repeating a trial, high precision would mean you're getting basically the same measurement each time. Precision can also be used to describe the instruments we are using to take those measurements. So for example, a scale that can read to the nearest gram is more precise than a scale that can only read to the nearest half a kilogram. Accuracy is how close measurements are to the true or correct value. In general, when we're doing a lab, we would want to have high precision and high accuracy, because that would mean we are consistently getting very close to the correct value. Last term here is percent error. This is something you'll be asked to calculate on several different labs. It's a good way to sort of check how well you did with your measurements. So to calculate percent error, you'll find a lot of different equations. These terms are written in a lot of different ways depending on if it's physics or chemistry, and it even varies within a subject. So I've written it here as the absolute value of the actual value minus your experimental value. So actual here means the correct one. So actual minus experimental divided by the actual value. You can think of that as like dividing by the correct answer. And then times 100%. Sig figs, again, sig figs, you'll need to know for this chapter how many sig figs are in a value. After this chapter, you just need to be able to provide an answer that doesn't have, way too many sig figs. So the dry rules for sig figs, any non-zero digit counts as a sig fig. So 1, 2, 3, 4, up through 9, those are all sig figs. Any zeros between those non-zero digits also count. So if a number is 504, 504, all three of those digits count. And the third rule is that zeros to the right count only if there is a decimal point. And it's important to note it doesn't matter where the decimal point is in the number. So it doesn't matter if these zeros are coming before or after the decimal point. If there's a decimal point, any zeros to the right of non-zeros count. If there's no decimal point, then zeros to the right do not count. Notice that zeros to the left are not mentioned, and that's because zeros to the left never count. So it doesn't matter if there's a decimal point. The other rules you might use are listed over on the right side. So this is sort of a different method. It's called the Atlantic-Pacific method. And here we're just checking if there's a decimal point that is present or absent. So the A for absent corresponds to Atlantic, P for present corresponds to Pacific, and there's a little map just to help you understand how this works. So if the decimal point is absent, that means we're thinking of Atlantic, and the Atlantic Ocean is over on the right side of the US, so we're going to count from the right. And you start counting when you reach your first non-zero digit, and then you count all the values after that. If your decimal point is present, then P Pacific, that means we're going to count from the left. And again, you start counting once you reach your first non-zero digit. If you want to practice, if you're not confident with sig figs, you can follow this link. It has you type in, the number of sig figs for different values, and it will tell you if you're correct or not. One thing that isn't on here, if you have a number written in scientific notation, so if it's written as 5 times 10 to the third, it's only the number out front that counts for sig figs. So that 5 is what matters. The 10 to the third part we don't worry about at all. SI units, so the SI stands for the International System in French. And there's 3 fundamental SI units for us that measure length, mass, and time. They're the meter, second, and kilogram. And note that we use kilograms in physics, not the gram, so that is different from chemistry. If you're given a mass in grams, in this class you'll generally have to convert it to kilograms before you plug it into the equation. This table lists some base units. There are other units that you can derive from these. Base units, meter and second. If we take the ratio of those, if we have meters per second, that is a derived SI unit for speed or velocity. Prefixes you'll also need to be familiar with. What can be tricky with a prefix is, it's written typically with a letter, and that letter comes right in front of the unit itself. So for example, if we had megawatts, we would write that as capital M, capital W. And it's not always obvious, if those letters are representing just the unit or a prefix with a unit. So you'll need to be confident and recognize these prefixes. We typically use giga, which is 10 to the 9th, down to nano, 10 to the negative 9th. And most of these are English letters. There is one Greek letter for micro, that sort of cursive looking M or U. It's pronounced mu or mu. You'll hear both pronunciations. And by the way, we mispronounce a lot of things in physics, so don't expect that the pronunciations you hear are how you would actually pronounce those letters or words in the native language. All right, so here we have our first example problems. Periodically throughout these lectures, there will be example problems. I would recommend you pause the video, answer the example problems, and then continue the video once you're ready to check your work. All right, so for this first problem, we have a capacitor that's labeled 2.5 microfarads. How would it be labeled in just farads? And farads is our SI unit for capacitors. We'll cover that in the second semester. So 2.5 microfarads, if we replace that prefix with the value it represents, we could write that as 2.5 times 10 to the negative 6 farads. So we've just replaced our prefix with the actual 10 to the 6 or negative 6 value. Next, we have a radio station that has a frequency of 106.7 times 10 to the 6 hertz. We're going to write this in megahertz. So again, we replace now the value with the prefix, so 106.7 megahertz. All right, those last two examples were fairly easy because the exponent matched one of our prefixes from the table. Here, you'll see that if we were to write these all in scientific notation, it wouldn't necessarily match. So this one's a little trickier, so go ahead and pause the video, see if you can come up with the correct answers. All right, for A, 3.02 times 10 to the 7 watts. Since we don't have a prefix for 10 to the 7, at least not a commonly used prefix, what we would do is, if you imagine 10 to the 7 is really 7 tens multiplied by each other. So if we were to take out one of those tens, we'd have 10 to the 6, and we do have a prefix for 10 to the 6. But we can't just take out a 10 and have it disappear. So we have it multiply by that number out front, the 3.02. So we have 3.02 times 10, so it becomes 30.2. And then we're left with times 10 to the 6, which we can write as megawatts. For B, if I wrote that in scientific notation, I could have 5.13 times 10 to the negative 2. That is a prefix on our list, but it's actually very, very rarely used when we're talking about amps. So centid, that prefix is used obviously a lot with meters, so centimeters. It's used with liters, not used very often with amps. So I want to write this in a prefix that's a multiple of 3, in this case 10 to the negative 3. So if you just imagine moving that decimal place over 3, you'd end up with 51.3 milliamps. And our last one, this would be written as 7.05 times 10 to the 5th joules. Again, I'm just going to picture moving the decimal place over. So if you move it over 3, you're left with 705 kilojoules. If you moved it over another 3, you'd have 0.705 megajoules. Generally, we want that number out front to be between 1 and 1,000. All right, so some of the math that's important for this class is really basic trig or geometry. So sine, cosine, and tangent are all important. We'll use it regularly throughout the course. Pythagorean theorem we'll see a few times, a squared plus b squared equals c squared. It's also nice to understand how similar triangles work and both complementary and supplementary angles. Algebra is super important. We do a lot of equations and a lot of manipulating those equations prior to plugging in values, or we may not even have values. We may need to leave everything as a variable. So manipulating equations is important. The quadratic equation we'll see a couple times. Generally, you're not going to have to solve using a quadratic equation on an exam. So you'll just typically see that on homework problems. And you are allowed to use graphing calculators in this class, including on the exam itself. So if you have a quadratic equation solver, go ahead and use it. It's not an issue. You just need to recognize that you have a quadratic equation, and so you can use a solver to find the roots or the answers. Logarithms are not super big, but we will touch on them briefly. And then again, Appendix A has sort of all the skills, the math skills you need for this course. Next, so SI units are very important. So what if you have a value that's not written in SI units? You'll want to convert. And we'll also use dimensional analysis to convert from values that are written with a prefix. So for example, if we have grams, you can use dimensional analysis to change that to kilograms. More often we're using dimensional analysis to change from non-SI units to SI units. So here we have another example problem. It says, would a driver going 15 meters per second in a 35 mile per hour zone be speeding? So go ahead and pause the video and then resume when you're ready to check your work. All right, so to solve this, we have two options. We can either convert 15 meters per second into miles per hour, or we could convert 35 miles per hour into meters per second. Either process would work. So I'm going to go ahead and convert the 15 meters per second into miles per hour. So this involves two different conversions. I have to change per second to per hour. So I've written all of the fractions as vertical fractions, so it's easier to see what values cancel. So seconds cancel out, we're left with per hour. And then that second fraction in parentheses is to convert from meters to miles. If you didn't have that conversion factor memorized, don't worry about it. And we're left with 33.6 miles per hour, so that's under the speed limit. Last, we're going to talk about graphing, and graphing is super important for this course. The AP exam you should expect to have some graph problem. Most likely you are either describing how you would graph something or you're analyzing a graph that's given to you. So in general, the independent variable typically goes on the x-axis and the dependent variable goes on the y-axis. However, we will not always do this. We will regularly switch that because by switching it, it gives the slope meaning. So often we will switch those values. Typically, we will put whatever variable on whichever axis makes the most sense. We will even sometimes manipulate those variables before we graph it, and we'll talk about that more later on. So we may square the variable first. When you graph things, it's important that you label everything. So label your axes, make sure you include units. When you are labeling the axes with values, make sure you're using an appropriate scale so that your data takes up most of the grid that you have. And make sure that your scale has equal values, right? So if you're looking at this grid, you want each square to represent the same amount. All right, so kind of 3 key things when you are looking at a graph to analyze it. And the first I didn't actually write on here, but that's just to make sure you take a second to look at what is being graphed and look at the values and think about what they mean. So for example, this graph here, we haven't really started talking about motion yet. We will coming up next chapter. But this graph is showing an object's velocity versus time. And if you notice, the graph starts at 0, 0. So if you think about it, that tells you the object has 0 velocity initially, or the object starts at rest. All right, so important to look at the graph first, think about what it means. The other things that we will do a lot with graphs is we will look at the slope and the area. For a velocity time graph, both of these things have real world meanings. So the slope you should think of as a ratio. It's the change in the y-axis over the change in the x-axis. If you're taking calculus or you've already had calculus, it's the derivative. And instead of thinking of it as y-axis divided by x-axis, make sure you think about what's actually on those axes. So for this graphic, for example, it would be the change in velocity over the change in time. And you may already know what that gives you. We'll also look at the area. And the area is the area between the graph itself and the x-axis. So for example, on this graph, we have an upside down triangle, and then we have a trapezoid. So that area also has a physical meaning. When we're finding the area, we're finding essentially the product of the y-axis and the x-axis. And again, in calculus, this would be the integral. All right, so probably the most important thing for analyzing graphs is typically finding the slope. So when you are finding the slope, it is very, very important that you use 2 points from the line of best fit. Do not use data points. If you try to use data points, you will likely not get full credit. So what do you do if there's a data point on the line of best fit? Can you use that data point? Yes, but I would specify in your answer that you are using that point from the line of best fit, not that you're using that point from the data table. All right, so here we have our last example problem for the day. It says determine the slope of the graph shown. So again, pause the video and resume when you're ready to check your answer. All right, so first, when I'm solving this, to make sure I get full credit, I would write using the points, and then I'm listing 2 points. So I'm using 2 and 1.5, and then 6 and 4.5. So those are 2 points on my line that appear to go through, across on the grid. So I have nice, not whole numbers, but close. So the slope is the change in y over the change in x, or the change in this case, velocity over the change in time. So I can do my y2 minus y1 values over x2 minus x1, and we end up with 0.75 meters per second, or 0.75 meters per second squared. So that is the slope for this line, and that would tell you the object's acceleration.